Small gas jets silently escape from the service module of a white capsule against the indifferent black backdrop of space. What happens when an 8-day mission loses its way home? Data recorded from the Boeing Starliner's thrusters revealed a progressive mechanical failure that transformed a swift flight test into one of the longest and most unexpected stays in the history of the International Space Station. The cone-shaped capsule, christened Calypso, approached the orbital complex at a relative speed of just a few meters per second. Inside the pressurized cabin, bathed in the soft bluish glow of digital control panels, two veterans of space exploration intently monitored the telemetry screens. The constant hum of life support systems filled the environment, while zero-gravity indicators floated freely tethered to the panels. The mission, formally designated as the Crew Flight Test, was meant to be a short-distance sprint, a rigorous qualification flight meticulously planned to last just over a week, designed to definitively certify a new human transport vehicle for low Earth orbit. But orbital mechanics forgive no margins for error, and the absolute vacuum accepts no thermal compromises. Just 200 meters from the Harmony module's docking port, the ship's sensors began to register critical anomalies in the helium system pressure. Tiny valves designed to control the precise flow of propellant to the directional engines began to fail in sequence, suddenly interrupting the thrust needed for fine approach maneuvers. What should have been a demonstration of impeccable engineering and a swift return to Earth's surface evaporated into the silence of orbit. The hatches finally opened with a heavy metallic sound. The astronauts floated into the familiar, well-lit environment of the station, and the countdown for their return was suspended indefinitely. Orbiting at 400 kilometers altitude, this colossal laboratory that is the International Space Station depends on a constant supply line. The indefinite suspension of the crew's return brought sharp focus the very nature, complex history, and inherent risks of the commercial crew program. For almost a decade after the definitive retirement of the Space Shuttle fleet in 2011, the American Space Agency relied exclusively on Russian Soyuz vehicles to access the orbital complex. The commercial program was created in 2014 to return this critical launch capability to American soil, establishing billion-dollar contracts with two competing companies to ensure redundancy in orbital access. SpaceX achieved the operational objective years earlier, establishing a reliable routine of crewed flights with their Dragon capsules. If you've made it this far, it's worth subscribing. Each week, a new expedition to the cosmos with real NASA data. Boeing, however, faced a series of profound technical delays, software anomalies, and uncrewed test flights that revealed complex structural failures over the years. The current mission was the final development milestone, the definitive and highest-risk test with human lives aboard to prove that Starliner was ready to undertake regular transport operations. For this monumental task, Barry Wilmore and Sunita Williams were chosen, two former United States Navy test pilots with thousands of hours of flight hunt accumulated across dozens of high-performance experimental aircraft. Both had previously commanded the space station on long-duration expeditions, intimately familiar with the relentless environment of microgravity and rigorous emergency protocols. On June 5, 2024, the main engines and solid rocket boosters of the Atlas V rocket tore through the sky from the launch pad in Florida. The brutal acceleration crushed the astronauts against their seats as the capsule breached the denser layers of Earth's atmosphere, leaving a thick condensation trail behind. Insertion into preliminary orbit was mathematically precise. The solar panels unfolded perfectly to capture sunlight, and the ship finally seemed ready to fulfill its engineering promise. But the complex propulsion systems harbored an invisible thermal vulnerability, one that rigorous ground tests subjected to Earth's gravity and atmospheric pressure had failed to fully reveal. The capsule's cylindrical service module houses an intricate network of 28 small directional thrusters. It was within this physical architecture that the thermal vulnerability began to manifest critically during the complex 24-hour orbital chase. To reach the space station, which travels at hypersonic speeds, a ship needs to execute dozens of small engine burns, altering its altitude and velocity with surgical precision. These fine adjustments are controlled by the reaction control system, metallic structures arranged around the hull that fire short jets to orient the vehicle. They use highly pressurized helium gas to force the liquid fuel components into the combustion chambers, where the fluids instantly ignite on contact. Even before ignition on the launch pad, engineers had already detected a small helium leak in one of the pressurization system manifolds. The anomaly was extensively debated by control teams and classified as acceptable, a calculated risk that remained comfortably within the mission's operational safety margins. But in the relentless, frictionless environment of space, the thermal behavior of pressurized fluids and metal alloys changes drastically under direct sunlight. During the final approach phase, as the capsule executed braking maneuvers to dance around the orbital complex, the system began to degrade rapidly. 5 essential thrusters simply shut off unexpectedly, refusing to ignite when commanded by the ship's computers. The autonomous flight software detected that the actual physical thrust did not match the mathematical trajectory calculations and cut power to the engines for safety. The capsule was temporarily paralyzed in the dark, floating 200 meters from the docking port with the curved immensity of Earth spinning just below. Wilmore took manual control of the ship using the rotational hand controller and deactivated the automatic approach protocols. He fired the remaining thrusters in short, precise sequences to assess the vehicle's dynamic response, a practical orbital survival test conducted in real time. Docking was finally completed over an hour late, and the metallic sound of the capture latches closing echoed through the station's hall. The crew was greeted with floating hugs by their expedition colleagues, and the ship was connected to the station's power grid, seemingly stable and safe for the moment. The telemetry screens in ground control rooms began to display mountains of flight data captured during the approach. But the relief of mechanical docking was short-lived, masking a much darker reality hidden within those digital records. Engineering teams quickly discovered that the helium leaks had silently multiplied and spread throughout the service module's architecture. From a single failure point identified before launch, the system now bled pressurized gas from 5 independent and structurally isolated locations. What if the ship's true test was to prove it shouldn't bring its crew home? The most critical and urgent problem wasn't merely the gradual loss of helium needed to pressurize the propellant tanks. The erratic behavior and thermal shutdown of the thrusters demanded a deep physical investigation that simply couldn't be performed in space, where zero gravity prevented component disassembly. The space agency ordered emergency fire tests at the White Sands Complex, an isolated desert in New Mexico dedicated to rocket propulsion testing. There, thrusters identical to those installed on Starliner were placed inside enormous steel vacuum chambers and subjected to the same extreme flight conditions. Engineers simulated the exact pulsing burn profile the capsule executed during the stressful manual approach to the station. The analysis results revealed a structural design flaw induced by the confinement of heat generated by the flames themselves. The extreme heat generated by continuous close firings was melting and expanding tiny Teflon seals located inside the flow control valves. These seals, swollen by the accumulated heat that couldn't dissipate in the vacuum, partially blocked the oxidizer passage, instantly suffocating the engines. The capsule anchored at the station still had enough liquid fuel and pressurized helium for the journey back to the atmosphere, but no one in the control centers could mathematically guarantee that the engines would function symmetrically during the critical, irreversible deorbit burn, the maneuver that breaks the ship to begin its fall. An asymmetric failure at that exact moment could send the ship into an uncontrollable spin, making it impossible to correctly orient the heat shield against the re-entry plasma. Or worse, it could result in too shallow a descent angle, causing the capsule to skip off the upper Earth atmosphere and be lost in deep space forever. The meeting rooms at the space agency headquarters in Washington became the stage of exhaustive debates on risk models. The unacceptable danger of an atmospheric skip forced mission administrators to an unprecedented technical and ethical crossroads in the era of commercial flights. During weeks of tense analyses, the space agency and the ship's builders debated the mathematical probabilities of a catastrophic failure during re-entry. The builders' engineers argued vigorously, based on software simulations and historical data, that the ship was safe enough to execute the crewed return. But the agency's rigorous safety culture, deeply and painfully shaped by the irreparable losses of Challenger and Columbia, would not allow human lives to be wagered on divergent data and unpredictable systems. On August 24th, the final and irrevocable verdict was announced to the world. The Starliner would return to Earth's surface completely empty, relying solely on its autonomous computers. For Wilmore and Williams, the decision fundamentally altered the physical, logistical, and psychological reality of the mission they had accepted months earlier. They had launched from the pad in Florida with personal supplies strictly limited to just 8 days in space. They brought light cotton clothing, specific test equipment, and a mindset focused on a very short duration qualification flight. Now they needed to instantly and organically integrate into the orbital laboratory's regular long-duration crew. Their stay was officially extended to the end of February 2025. 8 days of concentrated mission abruptly transformed into almost 9 months of continuous orbital expedition. They did not possess emergency spacesuits compatible with the other ships docked at the complex, creating an immediate and complex logistical challenge for the planning teams. Breathable oxygen, recycled water from life support systems, dehydrated food rations, and even improvised sleeping bags in the Columbus module, everything needed to be rationed and recalculated. In September, the Starliner capsule autonomously undocked from the orbital port, slowly moving away from the illuminated complex. It initiated its return burn in the absolute vacuum, with no one on board to monitor vital systems or correct trajectory deviations during the fiery descent. The capsule plunged into the atmosphere and landed safely in the desert with the help of its large parachutes, but the service module was discarded as per the original design. The thrusters that harbored the critical failures burned up and disintegrated completely upon re-entry, destroying the primary physical evidence with the scorching heat of atmospheric friction. With the loss of material evidence in the upper atmosphere, the two astronauts became permanently anchored in their new, prolonged orbital routine. What happens when an 8-day mission loses its way home? Human resilience takes absolute control of the situation, transforming a complex engineering setback into a pure demonstration of endurance and adaptation. The space station, originally designed as a frontier scientific laboratory, proved to be the most advanced, well-equipped, and safest lifeboat ever built by humanity. The test flight crew wasn't trapped in the sense of immobility, inertia, or despair faced with prolonged isolation. They were formally and actively integrated to Expedition 72, becoming essential members of the giant floating complex's daily operation. They immediately took on critical preventative maintenance tasks, conducted dozens of new scientific experiments in microgravity, and repaired vital life support systems that ensure the survival of everyone aboard. Mental and physical adaptability replaced the need for an immediate and risky rescue. They will return to Earth only in the following year, traveling in a competing company's Dragon capsule, occupying 2 seats that were launched with weight ballast exclusively to retrieve them from space. The mission that was meant to prove the mechanical and commercial redundancy of orbital access ultimately proved the invaluable worth of flexibility and human cooperation in the face of the unforeseen. In our next episode, we will investigate Yuri Gagarin, the first human in space, and the secret leap the USSR hid. The enormous metallic structure silently crosses the Terminator line, plunging into absolute dark as Earth spins beneath its solar panels.